Welcome to theme 4.2, radioactivity. In this, the last theme of the module, we talk about radioactivity, the law of radioactive decay, processes of decay that result in alpha, beta, and gamma radiation, and radioactive dating. I recommend having the notes open as you watch this lecture and annotating on the notes yourself. And I recommend having chapter 42 of your Wiley text open as well, and pausing the lecture, having a read of that as we go, led by this lecture and the notes.
Radioactivity comes from a spontaneous process involving the nucleus of atoms. There are three types of radiation: alpha, beta, and gamma radiation. Alpha and beta radiation involve particles with mass. Gamma radiation involves particles that are photons. They do not have mass. They are high energy photons though, because they originate from rearrangements of the nucleus, which involves large changes in energy. Alpha radiations are helium nuclei. Beta radiation involves electrons or positrons. Positrons are the antiparticle of an electron. It's the same mass as an electron, but has a positive charge. So if we have a source, how would we know what was coming out of it? Well, if we pass the radioactive emission through a magnetic field as shown in this figure, then you'd expect positive charged particles to be deviated in a different direction from negative charged particles. So you can look back to the magnetic theme of this course and it will tie in nicely with that figure. And alpha particles are not very penetrating. They'll hardly penetrate the surface layer of dead skin on your hand. But if you ingest them or breathe them in, then they can be dangerous, because the alpha particles are then coming into contact directly with living tissue. Beta particles, a bit more penetrating, a few millimeters of metal, and gamma radiation penetrates a few centimeters of lead. Uniting all these three types of radiation is that they are derived from spontaneous rearrangements of the nucleus of atoms. But there's another thing that unites them as well. They can all ionize atoms that they come in contact with subsequently. So, coming into contact with living tissue, they can rearrange the structure of DNA, resulting in cancer. We can start from a straightforward statement that the rate of decay processes that occur in a sample, the number of detections you detect from a sample per second then, is proportional to the number of nuclei that there are in that sample. If you doubled the size of the sample, you'd measure double the amount of decay processes. Just from that straightforward statement then, we can say that the NDT, the rate of change of the number of particles in the sample, is on the left of this equation, and it equals minus a constant called the decay constant, lambda, times by the number in the sample. So the rate is proportional to the number in the sample. If we rewrite that equation, such we have n on the left and time on the right, we can integrate both sides of the equation. And if we do that, going from an initial population n0 to a final population n, the initial population at time t equals 0, and the final population is measured at time t, then we arrive at log n over n0 is minus lambda t. If you're a bit rusty on integrating logs, the integration of 1 over x dx, you might want to just remind yourself of that separately. Okay, so rearranging that logarithmic equation, we take the exponential of both sides, if you like. Then we have n equals n0 e to minus lambda t. We refer to a rate of decay, r, as a positive number for a sample that's decaying. So r is defined as minus the magnitude of the NDT. And if we put in the differential of n equals n0 e to minus lambda t into that equation, we get r equals n0 lambda e to minus lambda t then. So at t equals 0, e to the minus lambda t is 1. And we're left with n0 lambda. So the initial rate, r0, is equal to n0 lambda. The decay rate of a sample is often referred to as its activity too. It's the thing that you're going to measure with a detector, detecting the emissions from the sample. There's units for decay rate. A common unit is the Curie CI, which is given by 3.7 times 10 to the 10 decays per second. But the standard international unit for decay is the becquerel, which is 1 decay a second. A little easy to remember. N and R both decrease over time, and they decrease in an exponential way. Here's a graph of N as a function of time. And with an exponential decay, we can talk of half-lives. T half is the half-life. It's the time it takes for a sample to decay from any particular value to half that value. Well, if you take the new T0 as where that T a half is, then the time it takes to decay to half of that value, so to be a quarter the initial value, will be another half-life, and so on. And that is the characteristic of exponential decay. Going to our initial equation, at the half-life we have a population left that is a half of its original value. So n0 by 2 equals n0, e to minus lambda, and the time is t a half. And we can rearrange that now, cancelling n0 on both sides, to give t a half on the left equals ln 2, the natural logarithm of 2, divided by lambda, this decay constant. And ln 2, if you try it in your calculator, is 0.693. It carries on with more decimal places. Let's try a worked example. At time t0, a radioactive sample contains 3.50 micrograms of pure carbon-11, which has a half-life of 20.4 minutes. Carbon-11, what does that mean? That's the mass number 11. So carbon is 6th in the periodic table. It has 6 protons then. It must have 5 neutrons for carbon-11. The question is to find the number of nuclei, n0, in the sample at T0. Okay, to do that, we can start by finding the number of moles that we have. The number of moles in 3.50 micrograms is the mass here divided by the molar mass, which to 3 significant figures is 11.0 grams per mole. So we get an amount of moles there. To find the number of undecayed nuclei in this amount of carbon, we take that number of moles and we times by Avogadro's number, 6.02 times 10 to the 23 nuclei per mole. We get the number of nuclei that we have. For a second question, what is the activity of the sample initially and after 8 hours? Initially, R0 equals n0 lambda. We know n0 now. Lambda we can find from knowing the half-life, which is 20.4 minutes, but the units aren't given in an immediately helpful form. We need that in seconds, so we need to do a units conversion. 1 minute is equal to 60 seconds, so if we write what is in brackets there is equal to unity, then we have a units conversion. Minutes will cancel, and we will be left in something per second. Okay, so taking that rate now in something per second, which is becquerels, we have 1.09 times 10 to the 14 becquerel. What about the activity after a certain time here for 8 hours in? Well, again, hours aren't immediately useful. We've got to convert that to seconds. 3,600 seconds in an hour. Can do that conversion. And then taking the equation for rate that we talked about earlier. We've got the initial rate, which we found out just above there, 1.09 times 10 to the 14 becquerels. E to the minus lambda, which we've already found out, times by this time 2.88 times 10 to the 14 seconds, and we can get an answer. It's around 10 to the 7 becquerels. This is a question given in your notes intended for you to do, but we're going to go through it here now. Today, a radioactive ore G is found to contain a ratio of isotope number of Ga to Gb of 1%. How many years ago would it have been 5%? Well, if that ratio is greater some time ago, it means that Ga is decaying faster than Gb. And we're given the half-lives there for the two samples. Okay, we can write down two equations, one for each sample, referring to the decay number as a function of time. So for sample A, Na equals Na0, the initial number, e to minus lambda A, the decay constant for that sample, times by time. And we can write the same for sample B. How do we use those two equations? We can divide one by the other. I guess that's the step to realize. We know those two ratios are numbers. Na over Nb is 1%. Na naught over Nb naught, the initial ratio of those two numbers, is 5%. And we can rearrange that equation with t on the left. Everything on the right-hand side of that equation, we can determine from what's given in the question. The two ratios of those numbers we know, and lambda a and lambda b are given by ln2 divided by their respective half-lives. There is a typo there, I can see. It's meant to say lambda b there for one of those equations, and it says ln b. It should say lambda b. Okay, so we can put those two half-lives in, and then we find the time. If we just calculate 1 over lambda a minus lambda b, we can rearrange that to being a little more simple, and then putting that in. T equals everything we know on the right, comes out to being 2.9 times 10 to the 8 years. We talked in part 1 about stable nuclei needing more neutrons than protons. And in this graph of neutron number versus proton number, you can see stable nuclei as the black circles. They're lying on a gradient then greater than 1. Note that graph isn't starting at the origin, but you can see the gradient there. Nuclei that are not stable, given by the other colours here, and they're going to go through decay processes until they reach a stability. So until they're on that line of the black circles. So take the blue neutron-rich nuclei here, for example, these guys. These are going to move onto the black circles, and they do that by electron emission. We're going to look at that shortly, but in that process, a neutron turns to a proton in the nucleus. So we gain in Z, but we stay a constant N number. We move to the right. Ultimately, if we repeated that process, moving on to the line of the black circles. The other circles we refer to as being neutron light. They're going to undergo positron emission, in which Z number decreases by 1. So if we take an example here of Z number decreasing by 1, it'll move those guys onto the black lines here. Again, we're going to look at that process shortly. Also, alpha emission, which will decrease N by 2 and decrease Z by 2, will move us down in a gradient of 1, ultimately intersecting the black lines. So all those processes that we've talked about for either neutron-rich or neutron-light will move nuclei species onto the line of stability. We can write an equation for alpha particle emission. If we start with a parent nucleus X and a daughter nucleus type Y, the element type does change because the atomic number changes by 2, and the mass number decreases by 4, and we give off a helium nucleus. Here's a couple of examples. Uranium-238 undergoes alpha decay to produce a daughter product, thorium-234. That undergoes alpha decay to produce a daughter product, which undergoes alpha decay to produce radium, which is shown also here as the second example. Radium undergoes alpha decay to form radon. Radon gas is a gas that you may have heard of. It's a gas that's emitted by certain building materials, stone in some Irish buildings, and it's certainly something that we're very tuned into being watchful for in Ireland. Radon itself undergoes an alpha emission in its decay, and it's that can be a health risk because as a gas it can be breathed in, and as we said earlier, that can be extremely dangerous. We can calculate the energy released in any decay process, as we talked about in part 1, from knowing the mass defect. So if we take the parent and daughter product masses and the mass of an alpha particle, and then we times by that conversion factor we talked about from mass to energy, we can calculate the energy released by that process. Let's look at the equations for beta decay now. Beta decay can be undergone in 2 ways. We can produce an electron or a positron. First shown there is an electron, second is a positron. Where producing an electron, a neutron in the nucleus is converted to a proton. you can see that on both sides of that equation, the charge is conserved. Whatever the charge Z is on the left, the total positive charge of that nucleus, we have the same total charge on the right-hand side of that arrow. Charge conservation has never been shown to be broken. So it's a really fundamental law in physics. Positron emission, then the opposite must happen by charge conservation. We convert a proton into a neutron in the nucleus. We could simplify these equations to show that conversion, neutron converting to a proton P plus an electron. That is maybe an oversimplification though, because we don't see this process happening outside of a nucleus. It only happens within a nucleus. But for positron emission, then a proton turns to a neutron, as we said. And we could write it like that to simplify. But the same point has to be made. This only happens actually within a nucleus. We don't see protons turn to neutrons in vacuum. We've had in brackets there that they were incomplete expressions we were looking at. And if we're going to write the complete expressions, there is another particle we need to account for, and that's the neutrino. And that's shown as a new symbol here. There's an antineutrino and a neutrino. The antineutrino has a bar above it. Okay, well, counting for these two particles, those are now the complete equations. The simplified form, neutron turning to proton plus an electron plus antineutrino, proton turning to neutron plus a positron plus a neutrino. And if we write examples for that, say carbon 14 decaying to nitrogen 14 with beta emission, and nitrogen 12 decaying to carbon 12 with positron emission. Those would be complete expressions here. We didn't write an equation for gamma decay. There it is at the bottom of this summary table. It's quite straightforward though. An element X does not change in atomic number, so it stays the same element and mass number. But we write a star next to that element on the left of the arrow there because we're considering an excited energy state of that nucleus, and it decays to a more stable state of the nucleus. Consider it as a more stable conformation of those particles in the nucleus, if you like. And it emits a gamma ray photon as a result. We've also got in that table alpha decay, beta minus or electron decay, beta positive or positron decay. There's a fourth one there, electron capture, which we are not going to cover in this theme on nuclear. So you don't need to know about that right now. Carbon-14 is often used for the dating of organic materials. Carbon-14 decays to nitrogen-14 with a beta minus emission. We have to make some assertions about the initial amount of carbon-14 present in the sample. We consider that carbon-14 is produced by cosmic rays in the upper atmosphere, and that this is a process we can get a handle on. I mean, to first order, we can say it stays roughly constant over many, many thousands of years. In fact, we believe there are slight variations to the amount of production carbon-14, and corrections are all the time being improved for our carbon dating. But for our purposes in this course, we're going to say that that ratio of carbon-14 to the rest of carbon that you'll find around it is a constant value over time. So we're going to keep it really simple. And we're going to say that ratio of carbon-14 to carbon-12 in the atmosphere is 1.3 times 10 to minus 12. It's not something you need to memorize now. It'll always be given to you. Living organisms are continuously exchanging carbon with their environment, either through ingesting the carbon, like us, or breathing it in, like plants, or breathing it out, as we do. So there's a constant exchange of carbon with our environment. So we're going to adopt the same ratio, carbon-14 to carbon-12, as is in our environment, assuming that carbon-14 doesn't do any chemistry significantly differently, which, you know, to a good approximation is the case. So when an organism dies, it will no longer be absorbing this carbon-14. And so carbon-14 then starts decaying to form carbon-12, and if you leave that sample for a long enough period, you would end up with mostly carbon-12 in the sample. So we can look at the ratio of carbon-14 to carbon-12. We can start to tell the age of that sample when it stopped exchanging with the environment, basically. Carbon-14 has a half-life of 5,730 years. Again, it's not something you'd be expected to memorize. It's ideal to be analyzing nuclides that have a half-life that's approximately that of the age you want to know about for your sample. Carbon-14 with a half-life of 6,000 years is ideal for most prehistoric and historic dating then. If one wants to look at geological timescales though, carbon-14 decay would not be ideal. You'd have hardly any carbon-14 left at all after billions of years. So to look at the age of rocks, we will turn to other things. Potassium decaying to argon is one typical process that's used in the dating of rocks. And potassium, if I remember rightly, is atomic number 19, argon 18. So that will be a positron emission process, with a half-life of 1 billion years. Let's look at an example of carbon dating. We've got a 25-gram piece of carbon found in ruins. It's showing a decay rate, 250 decays a minute. And we're asked how long has the tree been dead. We can use that ratio of carbon-14 to carbon-12, R0 equals 1.3 times 10 to the minus 12 for this. We've got some knowledge about rate here. So if we rearrange the rate equation for T, start with that, we could say the time taken is given by the ratio of rates R over R0, and it's a matter now of calculating R over R0. So we can now go about working out what R over R0 is. That's R over lambda n naught for carbon-14, which is that denominator is equivalent to lambda R n naught for carbon-12, given that R0 is the ratio of carbon-14 to carbon-12 number. We can rewrite the denominator yet further in terms of number of moles, little n, and times Avogadro's number for carbon-12. So now if we replace lambda in terms of half-life, which is something we know for carbon-14, we can rewrite that equation for mass as well. Little m over the molar mass, capital M, is the number of moles. And we get that equation shown. Okay, so it's quite a, looks like quite a long process to arrive at R over R0, but we're there now. And we can put in the values from the question and for what we know about carbon. Note a couple of things about the values we're putting in. In the denominator there's a value of 25.0 grams put in as the value of carbon-12. That was the little m that we defined. That's the mass of the sample though, right? But it is also the mass of carbon-12 to a very high degree of accuracy because the mass, relative mass of carbon-14 is so small. We've also got to make sure that we're cancelling units top and bottom here. The ratio of two rates is unitless. We need the same units top and bottom here. And so we do need to do some units conversions, and they're done at the end there, so just take note of that. And that then gets us to an answer by putting that into the initial equation, taking the log of R over R0, negative T half over log 2 times that, brings us to an answer of 3,400 years.
In summary, we've talked about radioactivity, the law of radioactive decay, alpha, beta, and gamma radiation, and radioactive dating. It's time now to have a crack at the homework problems.